Department of Electronics and Communication Engineering at IIIT Allahabad. He received his doctorate from IIT Kanpur, and his broad area of research is photonic packet switch architecture, optical data storage, optical networks, and switching wireless sensor network. He has published more than 90 research papers in peer-reviewed journals, and he is also an active member of IEEE and OSA, and he has supervised many PhD students and MTech students, and also PhD and MTechs are under ongoing, many of students in process. So I would like to invite Professor Ravi Kumar Singh sir for delivering his lecture. So hello sir.
Hello Dr. Open, thank you very much for can I start, Dr. Open?
Yes sir, yes sir.
So first of all, thank you very much, Dr. Upen, for introducing me in such a nice introduction of mine, and also thanks to Dr. Akhilesh Tiwari, who has invited me to deliver a lecture in this renowned program. I think the second version is there, ATAL program. So we are very much associated, IIIT in this case. So today I was supposed to say something about photonics and other metamaterials. So yes, we can say that my area is not on the metamaterial side, but yes, we can say photonics is something which is related to me, and yeah, I can give something. Maybe some of you are familiar with those areas, some of you are not, but I think we have to go with that. So photonics and optics are, but like we can say, a great relation is there, we can say, because ultimately optics is generated from photonics. So today I will give you an introduction of a little bit different side of photonics. That we can say that okay, since we are generated the fiber, we have done all the sensings using metamaterials, using some properties of fiber. Now today I will also give you some brief history of okay, now we have the fibers, we have the channels in the fiber. So how we can able to transmit into the networks and how we can go with the network side. So we can say, I will give you a relation of this photonics with the network side. So I will have a PPT there. So I will just share my screen. The slides are visible, sir?
Yes, your slides are perfectly visible.
Okay, so as I have mentioned, it is photonics networks we can say, or we can say optical network. I think more or less remain same are there, because we can say that normally in the network side we are saying that either we can say network is optical network, or we can say network is all optical. Sometimes people also say photonic network. So there is a slight difference between these networks and optical networks are there. Like we can say that nowadays we are moving towards optical, but still if we can say that what is optics or what is optical network, so there is nothing, no information is there in the optics. Optical or optics is only a carrier, which is going to, like you can say, it is like a train. So it is not meant for any data. No data is going to be there available along with us in the optics form. Anyway, if you can say like a data, then obviously the data is like my voice is also a data, my music is also a data. Nothing is in the optical domain. But anyway, once we want to transmit it for a certain location, so depending upon the requirement, either may use optics or may completely rely on electronic domain or completely on the optical domain. That depends upon that what feature I want. So that's why when we are talking about a network where both the things are going to be there, like electronics and opticals are there, we are talking about all optical, we can say all optical or optical networks are there, and then there is a complete optical network where we don't want any conversion. Like we can say that in network sometimes we require conversion because in early days we don't have optical amplifiers. So there we can say that we want a conversion. We want to amplify my information into optical domain. But since there is no availability of optical amplifier, so we have to convert all those information into electrical signal. So here we can say that in that sense we can say that our network is not completely optical. So that's why technology has been changed, and now we have a chances of completely optical networks are there, because nowadays we also have amplifiers, various types of amplifiers are there, which can amplify my signal remaining in the optical domain. So I will give, like, as I have told, that this is something which is different from your regular courses which you have studied till now, because I was going through the topics which have been covered in this series from last 3 days. So this is something different which gives us some, what you can say, glimpse of networks. So we can say that if you talk about optical network, that's why if you see I have mentioned photonic oblique optical network, because if we can say photonic also, then still I am talking about optics, because there is nothing like you can say photon is traveling. Obviously, what is optics? Optics is a photon, because when we are having a bunch of photon, it becomes optics. So, photonic means we can say we are trying to also discuss about some conversion principle, that how we are going to convert from electrical to optical domain, and how we are going to generate the light, how we are going to detect the light. All these things are going to be there. But once light is there, then obviously we can say that how to travel, how to use that light is called as optical network. So that's why I have mentioned it in a very different way, like photonic oblique optical network, because ultimately when it has to form, it has to go into communication form, it has to talk in terms of optic form. So that's why we can say that I will cover these few things in my lecture of now, today's lecture of 1 hour, we can say. Uh, so I will go with a very quick information, then I will go in detail with few things which is going to be there later on. So optical networks, many of you are knowing to this. It is same type of network which we are talking in case of electronic case. Either it is bus ring topology or bus topology, whatever we are doing. Ultimately, it is going to be there which where I am going to connect my information. Like in the LAN system we are using in our campus or different campuses, we are using LAN, local area network. There we are using optical things. So most of you are aware, or we can say that it is going to be used as a we can say as a backbone network, like our spinal cord is there. So we can say it is like a backbone network which can be used as a backbone, because obviously optical network means fiber is never is going to be used for point to point communication. So there we can say we are going to use obviously the features or the properties which a person who is talking about the physics of fiber, whatever they will suggest us, we are going to consider all those things. But ultimately, when I am talking about network, there also I am worrying about the losses and other things. When I am going to connect all those optical devices, or if my signal is traveling in the fiber in the optical domain, then we can say, okay, I have to worry about the losses, I have to worry about the attenuation, all those information I have to worry about that. So we can say that it can generate or store data in the electronic form. And then fibers are essentially very thin. We all know what is optical fiber. So that's why we can say it is going to have all these features which can carry signals. And obviously we know that optics can carry a large number of channels depending upon the bandwidth. So we can say that, yeah, if we talk about photonics, so where is the photonics? We can say that yes, all those conversion things are going to be happen, where I am going to, like here I am going to convert my information from electrical to optical. So much I am generating a light. Here I am going to receive the light. It means I am detecting the light. Then I am going to convert into electronic domain. So as I have told that this optical network means it is going to be used as a backbone network, not like a telephone network or telephone device. It is going to be used for your point-to-point communication. No, it is going to work as a backbone. Like you can say, the LAN wire doesn't come at your room. When it comes to your room, it comes in a form of cable connection or copper wire. Or sometime it may also comes in a form of Wi-Fi cables, or using Wi-Fi you are going to connect with your device. So you are not able to see that particular optics in your daily life, but yes, it is there. So why it is going to be needed? Why we require optical networks, or from where this optical fiber has been? Because optical fiber was evolved, but ultimately why it has been needed in form of network? The reason is very clear that day by day we are in the demand of bandwidth. What is bandwidth means? We are going to accommodate more number of channels, or if we can say very specifically, we can say that we want to accommodate more number of what we can say users in the close vicinity, and I also want that those users didn't get any problem like we can say they should not complain, I am not getting signal, I have congestion problem, I have various of things are there. So that's why we can say that that is a demand which is going to be on the top. And to fulfill those demands, we are going to say that we are going to have such type of network has been evolved. So we can say that this tremendous growth of connected users which are going to be there, that is going to be we can say great importance is there. I will use this marker so that this will be more clear. Sometimes it will be there. Yeah, the tremendous growth we can say. Then we can say why we can say more and more bandwidths are there, because I want more data browsing. Obviously, not we can say we want more data browsing, but we want a speed. Okay, the moment I should click on any link, I should able to get that particular link open. Either it is simple link or it is any video or any voice. I don't want any delay because nobody has sufficient time to wait for a video to be opened out. So it means that's why we are switching from one network to another network. Like some people can say Geo is good, some people can say Airtel is good. But if you think about that, okay, they are not same in all the areas. Sometimes in some areas Airtel are going to be good. So it means that depending upon the number of users in that area, how much they are having, that decides this particular thing. But the ultimate goal is that, yeah, bandwidth is going to be required. As you can say, downloading a movie, video conferencing, all these required bandwidth. So we can say that all these are going to require the bandwidth. So existing copper cable is not going to fulfill my all demand. So it means I have to think about some larger bandwidth or some larger data rate. So then we found, okay, it is an optical cable which can be helpful in such things, because optical fiber has been evolved much back. We cannot say that it is the evolution of today, but yes, in form of optical network, recently we can say it is not, it has been think about later, because once they have found different types of or different bands where they are getting this attenuation much lesser. We'll also see later that is going to be there. So once we can say that they are, like we can say these are some of the advantages are there. That why we are going to do, why we are, means in order to fulfill these demands of bandwidth, we can also have achieved such advantages. What is that? Low signal attenuation. Like if you compare with copper cable, like we have copper cable is much lossy, if you know, as compared to fiber. As compared to fiber cable, we can say copper is going to be much lossy. Distortion is also going to be there in case of copper cable. Power requirement is also, we can say, all these three importance are going to be very high, and these three are going to be such a huge things that gives us okay, why can't we use opticals also? Then this is also very important, like small space requirement. Like you can think about okay, like you might have seen okay, one copper cable can carry only one single current. And that might you have seen in your home also, okay, one copper cable is there that can carry a current. But the same thickness, or we can say, but the same copper cable which I can see from my normal eye carry a single current, and we can say there's a fiber which is of thickness of what we can say much lesser than that, because sometimes we can say single mode fiber has a diameter of 10 micrometer. So we can say in those cases, such a smaller copper cable, such a smaller area or dimension is going to be used for more number of wavelength. So this space requirement is also going to be fulfilled by this. And obviously low cost is there. Here we can say one question, somebody can ask the question is why this fiber is going to be very costly, why we are going to use it. But yes, fiber is costly if I am talking about point-to-point connection. But if I am saying that if I am going to use for multi-user, then I can say, okay, this is going to be important. So in case of multi-user, it is going to be fruitful. But if I can say point-to-point user, obviously this fiber is not going to be that much important, that much going to be cheaper business, because each and every device of optics is going to be much costlier as compared to normal copper cable. But in case you can say multi-user communication, obviously when we divide per user cost, obviously this is going to be much lesser as compared to other. And this is also important, which we can say interference. So interference is also going to be reduced much as compared to copper cable. So I think we are aware of all this. So this should be, like we can say, devices and components are there. So optical fiber, roughly all of us know that in the copper, in the fiber, there is a core, then there is the cladding, then there is the buffer is there. Buffer is something. Sometimes we also call it as a coating. So this is some sort of figure is there. So obviously, whatever is looking like very thick, we all know, because all of us are in the same background, is going to be very lesser. So the diameter is in micrometers. So that is going to be there, which is going to, we can say, space things are going to be there. Means in the range of micrometer, it is going to accommodate more number of channels. Sometimes 10, sometimes 20, depend upon the or higher than that. So, and we all know that since it works on the basis of total internal reflections, and I think the same phenomena is also going to be used for sensing. Like we are, you people have also working in the plasmonics on, we have done lots of experiment on these particular topics. So there also we can say we are going to utilize these particular phenomena. So, but obviously today I'm not going to discuss about this plasmonics feature here, because I'm assuming some principles and then I'm working ahead of that particular point. Okay, I am assuming that fiber has so much property and fiber can provide so much sensing, and then how I can utilize the same fiber so for the network. So as we have talked about, it is a core where my signal flows. All the channels are going to be flown in this particular this core. So if you talk about in case of fiber communication, then we can say that data communication is possible in the optical network, and roughly we can say that it can carry the wavelength in the range of 1450 to 1650. I think most of us are aware that why we are using this particular things, because okay, the figure is there in the later slides. We can say that we have some sort of attenuation graph is there. If you can draw the graph, it is something like that. Okay, it look like this. Okay, because this is something somewhat near about 890. Then this is something about 1350 nanometer, and this is something about 1500 nanometer. And here we can say that the loss is there. So these are called windows. This is called first window. This is called second window. This is called third window. So, and these windows has been evolved after a certain amount of time. That's why, as I told, that this fiber business has been evolved in we can say long back. But slowly, what they have done, okay, using this particular window, this network business is not possible. Because at that time the wavelength is very lesser. We can say we don't have transmitters. We are having transmitters, but the properties are not there, features are not there, and the losses are much higher as compared to losses at this point. We can say loss is this much and loss is this much. So this dip is going to be arrived at this point. So the loss is very lesser on this particular nanometer. So that's where today's working is going to be happen on this particular feature. So this is something we are calling as a center wavelength. Okay, all these are wavelength. So that's where they are saying this is the third evolution or third generation of optical fiber is there, where I am saying that we are working. So this is the bandwidth of 1450 to 1650, having a center of is 1550 nanometer. So we can say that the bandwidth is 200 nanometer. Or we can also say that we can convert into, this is also called a span. So we can convert this into in form of wavelength by using the formula of L is equal to C by lambda. So obviously the same thing is also going to be happen. Data is going to be modulated, and then data is going to be sent towards the destination, and then at the destination the receiver extract the data from the incoming signal. So whatever process is going to be happen in the electronic form, the same process is also going to be happen in the receiver form. So am I audible properly?
Yes, sir.
Yeah, good. Thank you, sir. So we can say that, so these are the basic features are there. Many of you are aware of all these features, we can say. Okay, because we are ultimately, we are going to use these features for our network side. So if we can say that, okay, what is so good in the network side, why we are going to focus. So yeah, this feature of wavelength division multiplexing allows us, okay, we can go for the uses of this optical fiber in the in the what we can say in the backbone network. Because if we talk about a backbone network, it look like this. And then we can say that we have a small network, small like a ring network, but not exactly the ring. So we can say that the backbone networks are there, which is made of fiber, and all the small branches are there. Those branches are going to be utilized for further uses. So it means that it is meant for more number of wavelength, and if all those wavelengths are going to travel for a longer distance, then we want some technique which can be used for multiplexing. So similar to we can say similar to TDM and FDM. Why I'm quoting these examples, so that I should not have to explain. So we can say TDM and FDMs are something like that, which can be used for normal multiplexing. Here, as we can say that this particular multiplexing is going to be happen in the wavelength domain, and we can say that some lambda 1 to lambda n number of wavelengths can be clubbed if all these are meant for a particular distance. Then we can say that we want them, okay, we club all them and then we can send up to a certain distance together. So what is that? We can say in the network, divide the vast transmission bandwidth available on fiber into several different smaller capacity channels which are non-overlapping bandwidth. What is meaning is that, okay, if I can say I have this particular delta lambda is the bandwidth. If I can say delta lambda is the bandwidth is there, and I want n number of channels in that particular band. Like we can take the example of this particular band. Okay, 1550 nanometer is the central band, and this is the band of wavelength are there, and I want, and 200 nanometer is the bandwidth. Now I want 10 number of channels here. So I can say, okay, I can allocate, I can make them a spacing of 20 nanometers, and then we can work with that. And corresponding to all those wavelengths, I can have one channel. So this is a very rough example of that. So we can say same thing they want to say is that we divide the whole bandwidth into some number of capacity of channel. Means this n can be defined as a capacity, that how much I can handle at a time. Either you can say capacity, or you can also say that in terms of users. How many number of users are going to be there? Now again, I have to discuss the same thing in perspective of, if I can say, normal users. Like mobile communication is going to be happen nowadays. So if I can say, okay, in any region, suppose I have given connection to 1,000 number of people, that doesn't matter. What matters here is that, okay, how many people are there, how many number of simultaneous connections are possible. Because I am having my mobile, but if I am not calling somebody, it means that I am not utilizing the channel. So idea is that they are working on the basis of probabilistic nature. Okay, how many number of connection can be possible, how many simultaneous call can be possible. That is called as a capacity. So if that is going to be decided, then depending upon that, I can allocate those particular wavelengths. Sometimes this allocation can be dynamic, sometimes we can say we can provide the allocating. Okay, but we can provide this particular, so we can say that all these possible things can be possible on different number of wavelengths, and we can allocate them different wavelengths depending upon those particular requirements. Each of these channels can be operated at a moderate bit rate. We can say that can be either 2.5 to 40 gigabits per second. That depends upon application, that what type of application I want. Whether I am going to call somebody, so my call is video call or my call is normal call. That decides the data rate or bandwidth which I am going to use. Maybe I can vary in that sense. Like sometimes people can say, okay, you are doing a WhatsApp call, and if you are not getting proper connection, they can say, okay, please don't make a WhatsApp call, please make a normal normal WhatsApp call, which should be only audio only, not video only mode. So each of these channels correspond to a different carrier wavelength. Obviously, that's why I can say that okay, we can allocate, and when I'm going to club all these in the same channel, they will evolve to the technique of which is called as WDM. So yes, I'm talking about this particular band. Okay, this is the band. I think you will find this particular picture in various books, and various books has been given in the different, but they are more interested in the dip. Okay, what is the dip which I'm getting here? Yeah, here also you can say, if you can see, 1550 is the dip. So this is the bandwidth. This is the usable bandwidth is there. Means apart from dip, I can go up to a certain distance. And here also we can say that we can go up to a certain distance. So this is the bandwidth, means this is the usable, and I can allocate different number of users in that particular band with a proper spacing. It doesn't. That is also called as guard band. If you have you go in the network side, guard band means two channels maybe have spacing is there, and the reason is very clear for this guard band is that okay, we can say okay, signal properties may hamper. Why it may hamper? Because once it travels a longer distance, it may got distracted like this. So whatever the band I am going to use, it may take this one also. So most of you know the name, which is called as aliasing. The feature of aliasing, or sometimes they also give me the effect of ISI, inter-symbol interferences. So the similar phenomena, what is happening in the electronic signal, the same feature or same problem may also happen in the optical domain. So this feature may also be there. Signal your signal may disperse. This problem is called a dispersion. So that's why we can say that we also want a guard band, or channel spacing is also required. So the same thing they want to show here, and we can say the losses is there, and obviously we are calling dB per. That's why I told you when signal will travel for a longer distance, maybe some distance d, then this problem arises. Why? Because these losses have been defined as a form of decibel per kilometer. Means if I can say okay 3 dB per kilometer, if this is the value is there, it means that my signal of power p will become p by 2. If it will travel p by 2, if it will travel a distance of 1 kilometer. Means after traveling 1 kilometer, my signal will become half. So this is the something which we can say by which we can define. And I think maybe you are aware that this fiber is having ideal fiber. Not we can say a normal plastic fiber or glass fiber, which are very lossy. If I can say the ideal fiber, then ideal fiber has a loss of 0.2 dB, 0.2 dB per kilometer. It is the ideal I am talking about. I am not saying that this is a general. Normal glass fibers are having much more loss as compared to this particular value. Okay, so we can talk about what is the channel spacing or guard band is there. So I will not go in detail. I will just show you the picture, then it will become more clear. Okay, what is the channel bandwidth and what is channel spacing is there. So we can say that if we have what is here they have mentioned in form of frequency, as I have told. So if you convert this wavelength of nanometer, you will get this frequency in this form 193.3. These are normally coming in terms of terahertz. This is also terahertz. So we can say that this is 10 to the power 12. So sorry, 14. So we can say that in this case, if we convert these particular wavelength, so if you subtract this 190.3 and 190. So we can say the spacing is 0.1, we can say, or terahertz, or if we convert into gigahertz, this becomes 100 gigahertz. So we can say that this terahertz is 10 to the power 12, and if we convert this 0.1 terahertz into, it will be giving 100 gigahertz. So we can say that the spacing between the two band of walking is going to be there 100 gigahertz. And if we talk about the signal bandwidth, then we can say that this signal bandwidth is going to be there on of we can say 10 gigahertz like that. So they have mentioned here, okay, I can use the signal bandwidth up to 10 gigahertz, and then we can say we can work with the channel bandwidth which is called of 100 gigahertz. So the feature remains same. Okay, how we work with carrier frequency. So there is the carrier frequency is going to be there. Then we have the data. Obviously, if we talk about the information in case of light, so normally light feature is working in case of like a digital signal, because either there will be a light or there will be no light. So similar behavior is that okay, I can formulate it in form of digital signal, 0 or 1. So depending upon that, I can say okay, we can perform this modulation. And then once we can perform modulation, then we can say we can transmit our signal in form of these channels. So what is the role of these transmitters are there? Obviously, as I can say, they can resemble with the electronic signals that, or we can say electronic communication. So we can say that we are still we have a multiplexer in the electronic domain. We have this signals in the what we can say demultiplexer in the electronic domain. Only thing is that how they have been made, that feature is only going to be different. Otherwise, principle remains same. There also we are going to merge data. Here also I am going to merge data, and those who are supposed to travel a same common distance up to from one end to other end. If they are going to change, if they want to drop it, then obviously I have to change it. Similar to the train, like we have different types of trains are there. Like we have Rajdhani trains are there which can travel from Allahabad to we can say to Delhi directly. So we can say there are an number of people, those who want direct communication from here to Delhi. So obviously that communication is going to be faster also. Why? Because there is no stopping, nothing is going to be there. All of them are getting their seats there. Means we can say they have got different locations, and then they are going to be ported to the Delhi. But sometime it may also happen we have separate type of carriers are there, which may have different types of options. Okay, some people will go directly from here to Delhi. Some people will go from here to Kanpur. They will drop, and another people will go from Kanpur. They will take your same seat which you have left in the Kanpur, and then they will travel. So such type of things are there. Carrier remains same, and I am pushing different data. Like if I can say I am a data who has to be transported to Delhi, means I will provide a seat. The seat is what? Seat is a wavelength. I am providing that particular seat. That wavelength may change. That wavelength will remain same. Okay, that wavelength seat number 1 is fixed. Maybe data is going to change. Sometime I will be there. Next day some other people will be there. So it is similar to that what we are happening in case of optical communication. So multiplexer is there. So we can say we have the transmitter which can convert data and modulate the optical signals. Similarly, at the receiver side, I am going to demodulate. Then we have demultiplexers are there, which can, like we can say, we have n number of signals are going to there, and then all those signals are going to be met. Here we can say that if we have signals from lambda 1 to lambda n, here they will travel simultaneously, lambda n, and then again at the receiver side, they will be what we can say demodulated, or they will be routed on different carriers. Okay. Then we can say we have the routers which will direct the signal from source to destination. Like we can say in this case, this is source, and obviously this is the local source we can say. But actual source is somewhere here, and destination is somewhere here. Then comes, as I have told, add drop multiplexer, to add new signals optically to a fiber and extract the same signal. Let me clear one thing, that previously the same phenomena is happening, or to perform these phenomena, I have to go into the optical, I have to go into the electronic domain. Like I have given you one simple example. Okay, somebody is going to start his journey from Allahabad, and he boarded the train and deboarded from to Aligarh. Aligarh, some other person has boarded the same seat. So that is called as add a drop. Means I have been dropped at Aligarh, somebody else has been added on the same seat tilde. So this is called a feature. Now such things are not possible in optical domain. So the same thing is going to be happened in the electronic domain in the past. But nowadays it is going to be possible by having, like you can say, like we are having different types of devices are there. So this is the example of your channels. Like we can say all these channels are going to be there, and then they are going to travel in the same fiber. Obviously they are coming from different fibers or different sources, but here they will travel via same fiber. That is going to that is the advantage of this particular multiplexer is there. Similarly, I can say that okay, I have these channels coming, single fiber, 4 channels, and I am able to extract all those 4 information here. Then, as we have discussed, the feature of optical devices, where we can say that we can perform adding and dropping of these signals. So here we can say that we have all the 4 channels are there. C1 and C4s are traveling till the end. C2 and C3 are going to be dropped. Why dropped? Because suppose my signal travels from some location. Now few of them has to drop in the path in between. So it means that now C2 and the signals on these C2, C3, or we can say lambda 2, lambda 3. Now these signals has been dropped. It means that now these 2 channels are free. I can utilize them. So we can say that we can add another signal if we have on these 2 free channels, and then they will travel in the same fiber. So these are the advantage of, like we can say, more number of bandwidths are there. As I have told in the beginning, okay, how can I define this particular number? So we can say here I have been only 4. Depending upon the lambda and depending upon the channel spacing, we can say that this number can be more than that. So that is going to be decided later on. That those are the design features are there. I am not going to discuss all those design features here. So the same thing is mentioned here, that each output is there, that I am not going to read these. So each input to the mux is not connected to, the same thing they have mentioned here. Add-drop multiplexers using optical devices are called as OADM. This is a short form which is going to be used in the literature. You will find out optical add-drop multiplexer. So this is the block diagram, but how actually this happens, that we have to see. Here comes what we can say basic physics of fiber. Okay, what devices are there which can be used? Like in our earlier physics, we are studying gratings. We have studied gratings in our physics, but we are very worried about what actually it does. Some people can say, okay, it can work as the grating, it can distract the signal, but actually what it does, it gets n number of channels, and depending upon the channel spacing, depending upon the pitch of that particular distance between the 2 mirrors, I'm able to what we can say distract the signal, the path of different signals depending upon their path length. The different wavelengths are going to be clubbed at the same point as per the path length. So we can say that those are going to be used, means constructive and destructive interferences are going to be happen in the grating at various locations. So those features are now going to be used or can be used in this particular networks. So we can say that okay, such type of operations, because this is something which is going to be there in form of what we can say this is something which is what you can say theorem is there, but how we can able to complete it. So here we can say by using this particular component we can use it. So if you can see here, we are using, you can see this one fiber is coming. This fiber has so many signals are there, like you can say 1 2 3 4, like roughly 8 signals are there. Now if I can say that they are coming from some location 1, they have to go to location 2. Now one of the signal which is at this has to be dropped for location 3. So how I will take it out, because there is nothing, I don't want any conversion or any electronic conversion is going to be happened. So how I am able to extract, because it's a bunch of light, I cannot able to simply extract information. Like if you recall, you have copper cables are there. जैसे हम लोग we are doing our normal home कि okay, if I have 3-4 copper cables are there, I simply cut the wire and take, okay, I have to make out this green one, I will simply take green one out. Life is very simple, but similar thing is not possible in case of optics. So how we can do this? Obviously we have to do in a different way. So gratings are there. These devices which we have studied in our physics, they are going to be useful. What is the feature of grating is that okay, we can design the grating in such a way that it can pass all the wavelength except a particular one for which I will design it. So we can say that this grating has been designed to pass all such wavelength except the wavelength of 1552 nanometer. Now one additional feature they are using optical circulator in this case. Now we know that what is the optical circulator we can say, or we can say simply circulator. Why they have used term optical? Because circulator is very common word used in the microwave also. But again, you can say property remains same, feature remains same. Only thing is that how they have been manufactured for microwaves and how they have been manufactured for this optical domain is going to be different. So what is the feature of circulator is that I think just I will very quickly we can recall it. Okay, what is happening in the circulator? If we have 3-port, 1, 2, and 3-port circulator is there. So whatever signal comes from at 1, it goes out from 2, and whatever comes at 2, it goes out from 3. So this is the feature of this particular circulator. So we can use this particular feature here. So we can say that we are going to make this as the input port, means at port 1 I am going to make it this here at the circulator. So all signal will pass through these gratings. Now grating will reflect this signal of 1552. So it will again enter into the circulator from port number 2 and it will come out from this port number 3, and I will use a detector, maybe photodiode or some other type of my pin receiver type, APD or pin diode, depending upon my uses, and then I can able to receive my signal. So this is called as the dropping of signal at any point. Like I can say that okay, I want some other, like I want 1546, 1548. So I will change the property of grating. Sometimes we are also having tunable grating. Maybe we can have. So in those cases, we can also change it. So we can say that depending upon the requirement, I can change this particular thing, and I am able to extract any one of signal from it. So this is also called as wavelength selective dimers. Means I am only taking out one of them, not all of them. Because the normal feature of grating is also known as that it can also work as a dimmer. So here there is an example of dropping signal at 1552. So now we can say that okay, in this particular channel, the capacity is 8, and now I have removed one, so it becomes 7 only. So meaning is that okay, I still have the legacy of one more. Okay, at any point of time, maybe in future location, I can add one more signal on a free wavelength, because this is not the actual signal, this is only the carrier. So I can add any signal on this particular wavelength. So for that I can use some other device. I will see that how we can use the same grating may be used, because sometimes we can use the grating, it is bidirectional. So I can use the same grating, and by using a combination of 2 circulators, we can add it. And how we can do it, you can see it, that the same grating may be used. Here we can say that this grating is going to be meant for 1556 nanometer. So we can say 4 signals are coming on 4 different channels. So 1556 has been we can say reflected by these gratings or discarded by the gratings. So it will be reflected and will come again. It will be dropped out. And here we can say that by this circulator port, this will be entering here, and again it will be reflected out. So it will move and it will be added in this particular main stream. This is called as main stream. So some sort of the example which I have given, the example of train, the same example can be used, and then we can say okay, I am not making it free, or we can say I am utilizing the free channel or free wavelength for some other signal, so that I can provide maximum possibility, or I can provide maximum usage of the capacity which is available on the fiber. So this is some sort of the signals are there which can be used. We can, they have shown in a, like sometimes we can also use couplers for adding a signal. Like here we can say they are showing that I have taken out the lambda 2. I have taken out the signals on lambda 2. So lambda 2 is free. And then we can say, okay, I can use coupler. And simply I have added here. But there are some disadvantages of couplers are there. That's why we can say, okay, we can also use circulator also. Okay. Then there are another example of the same devices which we can use. Like you can see that we can use this tunable fiber grating. See, okay, I can pass it. Okay. Now, few more things are there. End nodes we can define. Yeah, similar to normal router, we can say we also have optical routers which can like what is router? We can say like we are familiar with the term routers. So routers are also called as some sort of, they are called as switches. Means it performs switching. Like sometimes you might have studied, there is something called routing tables are there. What is routing table? Routing table is nothing but it performs the, okay, it is coming from switch 1, or it is coming from wavelength 1, it has to go to lambda 2, or it is coming from port 1, it has to go to port 2. So these types of switching is going to be performed. So either we can say that it is going to perform switching, or it is going to perform routing. Means it provides different routes to a signal depending upon its destination. So that is going to be there. Okay. So this is some sort of communication which is going to be there for optical network. Why calling it point to point? Because now I am saying that it is the complete picture of the signal. Like we can say that when it is in transmitter domain, we can say here I have the data. So complete picture of, okay, I am sending my data and I am getting my data out. So but all those things can come in the picture, that is going to be there. So you can see the data is there. Data can be converted on a particular wavelength by a transmitter. Then by using optical mux, I am going to plug all those signals. Passing, obviously, when I am saying passing from various, means I am talking about a very large distance. That may be 100 kilo, 10 kilometer, 100 kilometer distance is going to be possible. Like sometimes we lay the fiber beneath the sea and let it be flown like from a longer distance. So such type of connections are possible. So for long distance communication, obviously the losses are going to be there. Like we can say to connect these points. So I have used this optical amplifier, like similar to our amplifier which we are using in our normal copper cable. So such type of things can be used there also. And then at the receiver side, I am going to use optical demux so that I can extract out my signal on different wavelengths, and then using different types of what we can say receivers, or we can say detectors, I can convert my information into fruitful form, and then whatever the form of my data actually, whether it is, like we can say, because normally we can say that if I can talk about my information, if I can say information is there, so information can be only in form of data or video or voice. Only these three forms are there, nothing else. These three are the actual form of data, or you can say information is there, which may be transferred or which may travel on this particular signal, on this particular carrier. So if such type of things are there, then obviously these communications or these fibers may also follow some sort of networks, some sort of topologies are there. Why? Because if I am talking about, okay, these receivers are there, so it means that those receivers can be capable of converting that particular, receiving that particular wavelength. Like similar to our antenna, what is happening in case of our microwaves, like if I am using any antenna, So that antenna has a particular wavelength, particular bandwidth is there. I'm not saying that I can receive all the signals. Like you can say, you can take the example of FM receiver. Right? FM signals are going to be transmitted at various frequencies, but it depends upon that what frequency I am going to tune it. So if I will tune it on different wavelength, I can able on different frequencies, I can get that particular FM connected. So it depends upon the device which I am going to use. Okay, so that tuning is going to be required. So we can say here also, we can say that if I have different wavelengths are there, which type of wavelength I want, so I want some sort of tuning is going to be there. So in here also we can say that if I want to perform those jobs, I should have these two types of networks are there, broadcast and select, and wavelength of the networks are there. I will not go in very detail of these things because obviously these are not very much of things are there. But since we are studying about the networks, so a brief history I will give you only. Like what they are saying, okay, I am having these 4 signals are there, and if I am going to pass through receiver, so simplest techniques what they follow is that okay, I club all these signals and then I will transmit all these signals to all the destinations and let the destination decide what signal I am going to receive. I think you are aware, or we can say the sign of this arrow is called as it is called as tunable. Like we can say okay, if I am using this filter, so this is called as FF, this is called as fixed filter. But the moment I put this arrow here, this becomes TF, tunable filter. Meaning is that I can tune it similar to your FM receiver. So here we can say that we are having 4 wavelengths are coming, but I want that my signal will not be that much complex. So what I will do, I will club all them and then I will transmit to all of them. So what actually I am doing here? I am doing here broadcasting. Broadcast means I broadcast the information to all these 4 users. Let the user decides what I want. So this portion is called as select. So this is called as broadcast and select networks. Okay, I broadcast my information to all of them, let the user define. Why? Because sometime user may require lambda 1, sometime user may require lambda 2. So depending upon the requirement, I can use it. So it means very clear that these broadcast and select networks are going to be very specific. It may be going to be user dependent, what user wants. So I will make it very simple. I just give all the things to them. Okay. Like we can give a very simple example of, okay, I will not go in that way. I will, because I think the time is, 4 o'clock is there. So I am limited with the time. So I think already I have discussed these things. So I will not go in the details of these linings because normally these lines are only just to go for a study of these things. So obviously, maybe it is unicast and multicast communication is going to be possible. Yeah, some sort of broadcast and select natures are again we can say here. Second is called as wavelength routed network. I will again show you the pictures. What is the scenario? Then I will go with the details. So we can say that what actually happening in this case. Now here you can see that we have n number of sources are there which can have signals are coming, and what I am saying that signals are coming from different on different wavelength. So what I can say, okay, I can just take them on different lines. I will just using demultiplex. Here I am saying they are using what electronic controller, as I have told that okay, this is going to control these devices, because ultimately obviously these devices are in form of optical, but controlling is going to be there electronic. So that's why we can say some sort of controller is going to be required. So if I am saying that there are K channels are there at all these sources, so I will make them to pass through this K, and then what they are saying that by using these gate switches, I am allowing them that whether they will, which path they will follow. Now you can see that they are going to use this particular delay lines, and depending upon the delay line, they are going to be passed through different wavelengths. means they are going to be routed as particular form of wavelength. But what happens ki, okay, suppose we have this particular wavelength is going to be there from here also, lambda 1. Lambda 1 is also coming from here. So if they will pass, all the same signal will move on the same line, then obviously one term is going to be there, is called as congestion. Okay. Congestion is going to be there. So to avoid congestion, sometimes we do this also. So what they are saying, we are using delay lines. Okay, if signals are coming on same wavelength, and since I am doing routing depending upon wavelength, so what I will do, I will allocate them different delay lines. Okay, if signal is coming on this, so lambda 1 is going to, one lambda 1 is here, second signal of lambda 1 will be here, third signal of lambda 1 will be moved to here. So what will happen, all these signals on lambda 1 will reach on this particular output after we can say after an interval. Okay, in first slot this will reach after second slot, this will reach after third slot, and this will reach after kth slot. So if all these informations will reach at their destination in different slots, so this receiver will not lose any information, or we can say that the loss in the system is going to be reduced off. So that's why we can say that such type of routing or such type of switching is called as wavelength dependent routing. Okay, and then last is called as like you can say that how we assign the wavelength to different what we can say different lines. So we can take the example of this particular, that is also called as routing and wavelength assignment. So we can say how we can do it. Okay, suppose we have 4 users are there, that is also called as end nodes. So if I am going to connect these 4 end nodes are connected in such a way, see how we can say that they can be connected on lambda 1. If 3 wants to send information, they can use lambda 2. Why lambda 1 again? Because there is no similarity here. And similar, we can say that if I want lambda from here to channel 4, I will use another channel. Why? Because lambda 1 is coming from this particular end node. So I will change the wavelength, lambda 2. Again, we can say that from 1 to 3, if I want to connect, I can use the same wavelength lambda 2 here also. Why? Because there is no problem here happening, because lambda 2 is not connected neither to this nor to this. Meaning is that by using simply 2 wavelengths, I am happy with the communication. Why I am saying that we have to save the wavelength? Because I want transmitter of such a wider wavelength or on different wavelength. So there is also going to be problem, because I don't have availability of so many different sources available for so many wavelengths. So obviously, if I want to connect here, if I want to connect 1 to 4, then obviously I have to do something different, which is lambda 3. But luckily this time it is not there. So you can see the same thing is happening here. So that is called as wavelength assignment, and how we can perform routing. That is called as RWA, routing and wavelength assignment. So these are the roles of routers are there, that how they are going to perform this assignment, or controllers are there which do this job. So we can say that these are the routers are there. So I can pass my information. So you can see these red lines are for lambda 1 and blue lines are for lambda 2. So we can say that we can use same fiber. You can see in the same fiber I have lambda 1, lambda 2 both. Since they are traveling on different lines, I don't have any problem. Similarly, from this router, I will pass it here, and I can pass here from here also. So, and since it is lambda 2 and this is here, we can say it is going to lambda 2, we can say there will not be any problem. And then similarly from here we can transmit to 3 to 4. So that's why we can say that we are having this all optical networks are there which can perform communication that is going to be there in the optical domain. No opto-electronic conversion is going to be happen in the intermediate node. That is what we can say, that is the advantage of what we can say all optical network is going to be there. And if such things are possible, then we can say, okay, we are happy with our communication part, or we can say we are happy with our what we can say optical network is going to be fruitful in that case. So this is all about for my today's lecture or today's discussion. If you have any things you want to ask, any queries there, then I am there to resolve. Thank you very much for this time and your patience.
Thank you, sir. Thanks a lot. Nice lecture. And welcome. Welcome to question hour.
Yeah.
Please, if anyone have any question, please, you are most welcome.
Maybe this topic may not be a little bit different, like you people are talking, because you're talking basically physics of fibers, but some sort of conversion is going to be required, so that's why maybe it is going to be fruitful. If some of you are interested in moving towards.
So, sir, there is one question from my side.
Okay, sir, please.
Because all the network, the optical network is basically, as I know, is based on these optical fibers, I think, these days.
Yes, sir, yes, sir.
So, and there is a number of lines have been used in our sea route, I think.
Yeah.
So how they are using to enhance the signal. If there is a drop in signal, so is there are devices inside there, or how do they?
No, actually, sir, in case of like communication via C, as I have told that C is the simplest things where we can perform our communication. Like we can say that in case of C, as I have told that okay, if I have to travel for longer, like I can draw things like this. Like we can say that okay, I think I don't have picture right now, but I can say if this is a C is there. So what simply people say, they can use that drop a fiber on the, what we can say, on the lower side of this particular things, and they simply put it in the sea, and from one part to another destination. Now what happens is that, as you are saying that if suppose longer distances are there, and some problems may happen, yes, like we can say signal quality degrades. So in that case, depending upon the length what I'm going to cover, we have different types of amplifiers are there. Like we can say we have pre-amplifiers, we have post-amplifiers, and we also have inline amplifiers. So these three types of amplifiers are also available with us, so we can use them so that we don't want to disturb the signal in between. Like we can say while designing, since we know the distance and we know all the properties which you people will give us, these are the properties. So while designing, we take care of which type of amplifier I can use.
Means if any power is required for amplification in between, then it is easy to give the power there. Eh?
Yes, sir. Yes, sir. Basically, light power is going to be there. Yes, we have to detect. Okay, what light power we are going to send.
Okay.
But yes, as we have told you, okay, same thing is not easily possible when I am using copper cable for communication, which is going to be tough in those scenarios. Means in this case, I can cover a very longer distance, which is not easily possible for our normal communication.
And one more little technical question. What is the loss these days? What is the maximum loss? Or I can say, what is the optimum loss we have created in our optical fibers, minimum value?
Sir, as I have told, ideal fiber has a loss of 0.2 dB per kilometer.
0.2 dB. Okay.
Which is, as I told, this is the very ideal minimum we can say, but this is normally not possible. 0.2 dB. Sorry, some problem is there sometimes. 0.2 dB per kilometer. This is the 0.2. So this is the minimum loss which is possible, but this is not possible by any end. Like if you can say in our lab, which is there in the building, in another building, normally for lab purpose or for different purpose, sometimes we use plastic fibers, sometimes we use glass fibers. like we can say in our lab we are using plastic fiber so that we can give demonstration to the students different types of losses. Otherwise it is not possible with glass fiber I can show anything because I will not able to feel any loss. So what should I do in that case? So these things are going to be there.
Okay. So thank you, sir. Thank you very much. If anyone have any question or even later on, please type your question or send us the question. We will slowly respond it. And let's thank Professor Rajat K. Singh sir for a nice talk and nice information about the optical networks and optical fibers. And perhaps it will help us to understand how the photonic crystal fibers will work in future. So thanks a lot. Thank you, sir. Thank you very much. Let's
Thank you, sir. Thank you very much. Thank you, sir. Thank you for giving me this time, and I hope we will continue such type of interaction later on also. Thank you, sir.
Okay, thank you, sir.
So shall I disconnect, sir?
Yeah, please. Thank you, sir.
Thank you.
So now the today's session is over at this point of time. So tomorrow is our last session. From morning we will start by the talk of Dr. Sanjay Singh from IIT BHU, and second talk is by Professor B.R. Sangpal from the NIT Nagpur. And after that we have a small validatory and feedback session, and perhaps we will prepare the some small questionnaires for feedback part. And I will also encourage all of you, if you have any kind of feedback, please send us.